Security researchers have found an unpatchable vulnerability that exists in the Apple A12 and A13 boot process. It is a vulnerability that is baked into the firmware of the phone, and you literally cannot patch it with software. You have to take your phone, throw it away, and get a new one for this bug to go away. This bug takes advantage of a vulnerability in the USB controller of the device that requires physical access to get into. And while this bug may sound kind of doomy and gloomy, it actually might be a net positive for the entire iPhone ecosystem. This bug is a vulnerability in the secure boot chain of iOS. What is secure boot? Secure boot is the ability for Apple to verify that the code running on the device is made by Apple. What it does is it starts with this thing called the boot ROM. The minute your device turns on, bada bing, bada boom, the boot ROM is running. The boot ROM is inherently trusted. Apple burns into the silicon and it says, hey, this is running on the device. The boot ROM is pulling up other pieces of code as the device boots up, and it's checking, is every piece of code signed by Apple? Did Apple write this? Okay, cool. And then this piece of code checks the next one. Did Apple write this? Okay, cool. It's going through and making sure that Apple boots up the device with only Apple code. This may sound like an evil corporate thing, and it might be in some scenarios, but generally from a security perspective, this is to prevent hackers from installing what's called a bootkit in your phone. If the hacker can control code at any of these levels, they can change the code in the OS and make the OS do malicious stuff. So by verifying cryptographically that all these steps are correct, you're trying to verify on the way up the chain that hackers haven't changed the code maliciously. Now, the iPhone has two boot modes. It has the normal boot mode, which goes up this process to make sure the device is loading properly to boot into the iOS kernel, but also, if you want to upgrade the firmware of the device not using over-the-air updates, if you want to plug it into your laptop and upgrade over USB, there's a mode called DFU, Device Firmware Upgrade. And as the name implies, over USB, you're receiving these packets from your computer to check to see if that code is cryptographically signed and uses that to replace the firmware on your device. Now, the only way for a hacker to invalidate this process, to make the secure boot not work, is if there is either a cryptographic misimplementation of code or certificates in this process, or if there is some kind of memory corruption vulnerability in the processing of this data that allows an attacker to change the data as the boot process runs. And this is exactly what Paradigm Shift found in not the Apple code, not the Apple A12 chip itself, but in the designware USB controller that is used by Apple in the DFU mode. Again, DFU is taking data off of the USB cable, putting it into memory somewhere, and doing something with it. This is to put new code in the device intentionally. And when the new code arrives, the boot ROM is still checking cryptographically, is that new code signed by Apple? But what if there's a vulnerability in the way that the USB controller parses USB packets? That is a bug that is so low level, it's the name of the channel, by the way, that it just, wow, chef's kiss, like absolutely glorious. Again, like bad news for Apple, amazing. Like the research here is absolutely glorious. We're talking so low level that this is a vulnerability in the parsing of USB setup packets, okay? Literally in the establishment of a USB data channel, okay? So again, go and read Paradigm Shift's blog post. There's a lot more data that I'm not going to cover here. I want to kind of just highlight the beauty of this research. But basically, the bug exists in the establishment of a USB data channel, okay? So as far as I understand it, to set up a channel, you have to send these two packets. It's a token packet and a data packet, and this constitutes a setup transaction. And according to the USB specification, this setup transaction must be exactly 8 bytes and adhere to this very strict format. Sounds well and good. What could we possibly do wrong with 8 bytes of data, you may ask? Great question. Now, to receive this data, all the data transaction is being done over DMA, direct memory access. I'm not going to go into a lot of detail about what that means, but basically it is a way for hardware to receive data out of band with the actual CPU cycle so that it can quickly just read the data without having to wait for like transaction speeds. Now, the way that you program DMA is over MMIO, okay, memory mapped IO. It's basically a way to program the DMA controller to tell the DMA controller where to put the data. When the data comes in off the USB line, where does the data arrive? Okay, so we program that address into this register here. Now, as you can see, the way that the DMA controller works is it treats the DMA region kind of as a ring buffer. So you receive 3 packets that are 8 bytes long, and you go through and get up to 24 bytes. And then once it's gotten to the end of this 24 bytes, it subtracts the region by 24. So basically you have a 24-byte ring buffer so you can receive 3 setup transactions. Very simple stuff. Aha! But the core issue arises because the controller also accepts smaller packets in 4-byte chunks. So what this means is you can send the controller only 12 bytes, but when it receives those 3 packets, it will then subtract 24. You can write behind this DMA buffer arbitrarily with USB data, which is just absolutely insane. Now, the question then becomes, what do you do with this? How do you turn a DMA overwrite in the heap of a controller into PC control? Well, I'm not going to go in the A13 very deeply because the A13 uses this thing called pointer authentication codes, which is like top-end hardware-enabled security that I would like you to read there right up for it because I don't understand it yet and I'm not going to pretend to. But for the A12, it's actually very simple. Literally, the region that the DMA space is allocated in is adjacent to the stack of the USB controller task, which means that all they have to do is write behind themselves a little bit, and they overwrite LR, which is the link register, the return address of the process or the task, and that allows them to control PC. Like they get code control at that point. Bada bang, bada boom. That's it. Literally, we're right behind yourself by a couple of those packet increments, and then ta-da, you have control of the device. Insane. And once they get code control, they have to go from what's called EL0 user mode in the Intel sense, and they have to go from EL0 to EL1 to get arbitrary code control and system mode so that they can do whatever they want. There's a whole process for this. Again, if you're an exploit developer and you're interested in this, go read the write-up. Very interesting stuff. I want to talk about what this actually means for the average person. Again, this is an unpatchable vulnerability in the A12, A13, but you need physical access. You have to come to my house and take my phone for this to be exploitable. What does this actually mean? Now, I want to talk about juice jacking for a second. There's this whole topic I hear about all the time. What is juice jacking? It's the whole thing where, like, if you go to the airport, don't use the public USB things because the public USB chargers could hack into your phone. Okay, bro, listen, that was true in like 2010. Okay, the world of exploiting a phone over USB is like basically dead, unless of course you're using like an OMG cable, which is a whole other world we'll go into. I don't want to talk about too much here, but there is a world where if the cable itself or the outlet itself is like very malicious, like things can happen. But generally, plugging your device into a USB outlet is like not a big deal. What can happen though, technically, I'm not saying I've observed this, I'm not saying I've even seen this happen in real life. Exploits like this that attack a device over USB are basically the only threat model for juice jacking, okay? Also, don't forget, to be able to exploit this, you have to be in DFU mode, which you have to hold your iPhone in like a very particular way and like push a bunch of buttons to get into this mode. So it's not even like very likely that you'll get exploited by this. The real only surface for this vulnerability is like if you are a political individual, if you are a politician, if you are a journalist, if you are somebody of interest to another foreign government crossing over a border where they may seize your devices. The whole point, literally, of the secure boot chain is to prevent somebody from inserting a bootkit into your phone and being able to do malicious shit, right? That's kind of the whole reason these boot processes exist. Now, unless there's, of course, a vulnerability in the USB handling of the device that allows a foreign government to take your device, plug it into a computer, and install arbitrary code, not so great, okay? But that being said, there's also additional layers, ogres have layers of security in the phone that like prevents this from being a real thing. At this point, if the attacker has used this vulnerability to get code on your phone, they have arbitrary code execution inside your phone and you're being detained somewhere, okay? What they then would have to do to get access to basically anything behind Face ID or passcode ID, they would have to then exploit a vulnerability in the secure enclave. Like inside of your Apple A12, A13 is an entire other CPU that is doing like cryptographic processes, and there's this whole other region called the secure enclave that they would then have to be able to run code inside of your CPU, exploit a vulnerability in that secure enclave, and then from there they could reveal your AES keys potentially in your device and use that to decrypt things, okay? There is so much bad stuff that has to happen for this to be like a real issue for the average person. But that being said, obviously the compromise of a secure boot chain is like not good. And I think the bug itself is beautiful. It's just for the average person, not like a huge deal, something you should be aware of though. That being said, to fix it, you have to get the Apple A14, which I'm not sure which phone that comes in, but you can go check that for yourself. And by the way, if you want to like test this bug right now by yourself, all you need is a Raspberry Pi 2350 that has a USB-C cable, and you can go to their site. I'll put the link in the description below. You can go to the POC, and then they show you literally how to flash the exploit into a piece of firmware onto your Raspberry Pi 2350 and then use it to exploit the phone. The proof of concept in the phone, by the way, is if you overwrite your USB serial ID with the 4 letters pwned, that confirms that they have code control on your device. Now, I'm not sure how much you trust this code base. I'm not sure, maybe you read all the code before you flash it, right? There's a whole world of trust we're doing where we're running this code arbitrarily and exploiting a boot process on our phone. That being said, the POC is there. You can go literally read what I just talked about, what they wrote in exploit.c right now. So go check it out. Hey, thanks for watching. Appreciate it. Goodbye.